In that case, good evening to everybody and welcome to tonight's meeting. It actually does seem a while since our last meeting, but it's great to get back onto our programme again. I have to say one of the definite pluses of this Zoom lark is that it spares us from being dependent on the weather outside and attempting to get, or probably not get, up the hill to the Mills Observatory, and so we can still enjoy our guest lectures. Tonight I only have one announcement, which is from Jim Barber, who has already received some contributions sent in for the Next Society newsletter. So if anybody would like to add to these, just send in whatever it is that you've come upon that you would like to talk about, and send it to myself or to Jim or to David, and we'll get it into the next newsletter. So to tonight's talk, I am delighted to introduce Pete Kuzma, who is tonight's guest speaker. Pete is currently working at the Royal Observatory, Edinburgh, in a postdoc post there. And he tells me he finished his PhD in Australia at the Australian National University. So he's having fun in the snow apparently now, so that sounds quite good. Tonight he's going to tell us about what seems to be a voracious appetite of our home galaxy, which seems to have consumed several unfortunate smaller galaxies, but in the process has provided information about galaxy evolution. So I will hand over to Pete to tell us about this, and to David, as usual, to do all the techie stuff. And catch everybody up later on. So over to you guys.
Right, yeah, it's ready to go. Everything's running.
Fantastic. Sounds great. Hello, everyone. My name is Pete, and yes, I am a postdoc at the University of Edinburgh. I work primarily with Professor Annette Ferguson, and I think Shaq Kohler, maybe Associate Professor now, Annalise Savali. And we do a lot of observational astronomy in the field of galactic archaeology. So much like how an archaeologist may study things in the ground, artifacts, bones, and try and piece together what life or what was going on in the environment at the time, we can look into the galaxy and look at different objects or features and try and piece together what was going on to create such a feature. And so the title of the presentation today is The Great Galactic Graveyard of the Milky Way. And this may sound a bit ominous, may sound a bit dark, but you'll see as we move along, it may not be as nefarious as you think. But the universe is a very beautiful place, I think. You don't have to look very far to see the wonder. I mean, all of you here are probably avid, keen astronomers. And I mean, if you can just imagine, I know it's cloudy, so use your imagination here. If you can imagine a clear sky, a clear night sky, you may see the moon as the most prominent object, beautiful, glowing orb in the sky. And you know, if you start going beyond the moon, you might see something, see the planets around, which are gorgeous. I mean, Saturn is what got me hooked personally in astronomy. I remember I was like 11 years old and seeing Saturn through a telescope, being this little small thing on the lens, but you can kind of see the gap between the rings and the planet. It's absolutely beautiful. Hooked ever since. And if the beauty doesn't stop with our planets. I mean, in the solar system, we get asteroids and we have some comets that with these nice tails as they enter and leave our solar system. That's start to drift out of the solar system, and you can see star clusters, stellar nurseries, and the beautiful environment that the Milky Way has just spread out everywhere. Absolutely gorgeous. And even if we step outside of the Milky Way, we can see dwarf galaxies. And this is it's a picture of the Large Magellanic Cloud. And being from Australia, the LMC is a very well-known object to us. And of course, the beauty goes even further. Spiral galaxies, elliptical galaxies, beautiful. It's such a wonderful science, and I'm very excited to be sharing with you all today what I've learned in the field of astronomy and galactic archaeology. But when you look at the Milky Way and you can see the night sky looks very tranquil. It doesn't look like there's much going on. It's just sea of stars, a sea of dust. It looks great. But there is something, it's not great. There's something evil lying beneath the surface of all of that. And you can't see it with the naked eye. We're going to need to go out and do some pretty fancy observations to kind of see what exactly is going on. I'm going to tell you exactly what this means. But before we get to the nitty-gritty of it all, we're going to have to go back, fill in some knowledge of how the universe began and how kind of expanded to how it is now. So if we go all the way back to the beginning of time itself, there is the cosmic microwave background, which you see here on the image. Now, this is probably a very well-known image. Most of you have probably likely have seen this. And this is the residue left over from the Big Bang. And the colors here represent density or temperature, depending what your flavor. The redder the spots, the more hot that area is, the more matter is in those areas. And it's in these areas where gas started to form, when stars started to form. And of course, a single star, not a galaxy, make. You need to add more and more stars, more and more gas. And it's in these density fluctuations where gravity started to take over and pull in more gas to create new stars. And over the course of the age of the universe, 13.7 billion years, are we able to go from the cosmic microwave background to the small seeds of stars to build up to larger galaxies to what we see today. Billions upon billions of galaxies. Very, very pretty, of course. But we're going to pick on the Milky Way mostly today. Actually, when I say mostly, all of it is picking on the Milky Way pretty much. But the Milky Way is a spiral galaxy. So when you look at a spiral face on, and you can see the spiral arms, the core, the dust, the gas, all of this, it looks very pretty. Now let's take this image of a spiral galaxy and kind of turn it on its side. And we can see something that looks like this. This is the Sombrero galaxy. And you can see that even though when the spirals are face on, the galaxy looks quite large, but when you turn it on its side, you look at it edge on, it's quite flat, with the arms or with the galaxy pretty much contained to a plane. And in the middle, you can see the core of the galaxy, this kind of bulge-like feature, where in the middle typically sits a massive giant black hole, and lots of star formation going on in there. This image here is kind of misleading. There is a lot more to a galaxy than just the disk, the bulge. So I have this schematic of the Milky Way, or the idea of what's happening in the Milky Way. So while we have the disk across the center with the galactic bulge in the middle, what I want to draw your attention to is what's labeled in the top left-hand corner of your monitor screen there, the term galactic halo. Now, the galactic halo is a diffuse spherical envelope of stars that embeds spiral galaxies, and it is typically very smooth. There's not much going on out there, apart from individual stars kind of sporadically laid about, all pretty much very old, as well as globular clusters, which are star clusters, tens of thousands, hundreds of thousands of stars, all tightly compressed into a single area of space. And these are not to be confused with open clusters in the bottom left part of your screen, which are star clusters as well, but they consist of a lot more younger stars, on the order of, say, millions of years old, instead of stars and globular clusters that are giga years old, billions of years. And we'll touch a little bit more on them moving forward. But what is a pretty fundamental question about this feature, and I guess this ties into the Milky Way in general, is how did the halo form? How did the globular clusters form? How did the disk form of the Milky Way, and how does that connect to the halo or the globular clusters themselves? It's all just kind of all linked together with just how did it all form? And so there have been theories of course, about this, and one prominent theory from the past was the primordial collapse, or a monolithic collapse of a gas cloud. So if you imagine just a great big ball of gas floating in space, and it can start to collapse in on itself, indicated by the arrows here in the top left. This cloud as well is rotating, and as the dust starts to collapse in on itself, stars start to form in all different pockets throughout the entirety of space. And potentially, if a gas cloud is big enough and there's enough matter there, theoretically, star clusters then would form. And as the dust cloud continues to collapse, more star clusters are formed, or more globular clusters are formed, and due to effects of angular momentum, the disk shape starts to take form, and all the remaining dust and gas keeps being pulling in further and further into the more disk-like model that we see today. So this idea of everything being formed out of one big gas cloud, it has some troubles to it when you consider the globular cluster, population of the Milky Way. See, under this theory of galaxy formation, if a galaxy has been formed out of the collapse of a giant molecular cloud, and if the Milky Way is very, very old, you'd expect that at the start of this whole process, that the metal content of the gas would be pretty low. Because at the start of galaxy formation, or the start of the universe, the number of elements that existed was basically hydrogen, a little bit of helium, and then just a significant amount of every other element, mostly lithium, beryllium, or boron. So you'd expect that the first stars to form in this suggestion, in this theory, would be very low metal content of stars. And over time, as the rest of this cloud began to collapse, the first stars would begin their own evolutionary life, stellar nucleosynthesis, and start fusing hydrogen and helium into heavier elements, eventually creating things like iron. And as they get older and older, they create iron, these stars explode, ejecting all of the elements that they've synthesized over their lifetime into the medium around it, into this gas cloud. So stars should, as the further and further into the cluster, further into the galaxy, as you go, you'd expect the stars to have more and more metal content. Metal is, I'm using metal in this sense to mean not only iron, but anything heavier than the element helium. So that should mean, if you look further and further out, lower metallicity stars, metallicity being another term for metal content. And the further you look into the disk section, the more metal rich you'd expect stars to be. And globular clusters should follow this exact same trend under this formation scenario. They do not show that. There is no, if you look at the metal content of globular clusters in the halo, they don't show this hypothesized gradient, if you will. So what's going on? What can we say? The disk may have well been created through this exact same process, but it doesn't explain the globular cluster population in its entirety. And even if you look at individual stars as well, it doesn't explain. So if you look at individual stars as well, they show the same thing. There is no metal content in individual stars as well. So this theory needs more work. Needed more work. And it wasn't until the 2000s did we start to get a better idea of what was truly out in the galactic halo. I mean, the assumption of it being kind of smooth, having not much substructure, was kind of turned on its head. So I want to introduce you to the field of streams. So this image, you're going to see this image so many times in this talk. I think I've included it about 5 times. And this is a part of the northern hemisphere sky. what you are seeing is a projected image of all stars from the Sloan Digital Sky Survey, data release number 3, I believe it was. And this image is brightly colored. So the brighter a pixel is on this image, the more stars that are in that image. And they've all been colored by distance, with blue being close and red, pardon me, being further away. So when you look at this image, you can see a lot of bright spots that are kind of sporadically placed around, and these are more than likely globular clusters or even open clusters, but chiefly globular clusters. But I would argue that your eyes aren't drawn to that feature. Your eyes are drawn towards this streak-like feature. If you can see my mouse, I don't know if you can, the streak-like feature that runs across the image here. Now, this is only part of the Northern Hemisphere sky. If we were to take this field of streams and expand it to this a much later version of the field of streams, you can see that this feature that you see in the middle wraps around. So in this image here, the disk of the galaxy is where these blue marks are. So we don't observe in there typically too many stars, too much dust, too much hassle. But in the other areas you see off the disk, you can see this feature. Now it comes up through the middle, goes down on the right. And if you're trained enough and can convince yourself, on the left-hand side, on the equator-ish area there, you can kind of see the stream again. So what is this? What is this feature? Now, I would like for you to imagine yourself as a dwarf galaxy kind of floating through space. And there are plenty of you in the universe. Dwarf galaxies far outnumber any other kind. But it does, because you are lower mass, you are more affected by the gravity of larger galaxies in your area, in your just vicinity of space. So it doesn't take long for you to start to feel in the pool and get caught in the gravitational field of a larger galaxy. In this case, consider, I don't know, the Milky Way. So in this, I'm going to show you a short simulation now. This image here is a representation of a dwarf galaxy, which is the glow bright yellow image in the top right-hand corner, and in the middle is an analog for the Milky Way. And this is what happens to a dwarf galaxy once it gets trapped in the field of the Milky Way. Its circular shape gets disfigured, it gets stretched, it gets destroyed. And over multiple orbits, the original circular shape will get stretched so much that it will form these what we call streams of stars that will wrap entirely around the Milky Way. This is, if you think about it, this is really quite a violent action. It's something this dwarf galaxy cannot, its internal gravity is not even strong enough to keep itself together. It just literally gets stripped, shredded apart. With the only thing that's able to remain compact or remain itself are systems inside the dwarf galaxy whose gravity, whose self-contained gravity is stronger than the pull of the Milky Way itself. And this could be such places like the core of the galaxy, star clusters of that galaxy. And for another nice representation of this is a more of a 3D view of this feature. This time the Milky Way itself is invisible. This is happening very quickly, of course, it's a simulation, but this can happen over a series of many gigayears. So as what essentially I'm saying to you is that feature that we're seeing in that image is the dwarf galaxy that the Milky Way is currently eating and is currently accreting. So this image, it's just something you have to know about the Milky Way, is that it's a cannibal. These large galaxies eat their own kind. They eat smaller versions of themselves, kind of like the bully in the playground. but just how many has the Milky Way eaten over its time? Like, is this object here, which we call the Sagittarius dwarf galaxy, the only one? Well, if we go back to the original image of the field of streams, there's a couple of other objects here in the image that could relate to a dwarf galaxy that the Milky Way has eaten. So with the Sagittarius stream right in the middle, and the circles there are surrounding globular clusters in the field of view, you're seeing that some of these circles lie directly on the stream itself. And the Monoceros ring on the right, the Hercules Aquila cloud on the left, the origins of these objects are not known. Palomar 5 in the bottom left-hand corner, we will touch on a little bit further on. Sit tight, it's very interesting what's going on down there. And you also have the orphan stream, which streaks right across up to down across the image. And the orphan stream is so called that we don't know where it came from, what its progenitor is. And so if you ever want to know just how creative astronomers are in naming things, I think you look at the orphan stream for an example of that. So when it comes to considering galaxy formation and this feature of galaxy, I mean, this is a natural part of galaxy formation. A galaxy only has so much gas, so much dust to start off with when it forms, and that's what this simulation is here to show you. It's how this process, how this occurs. A galaxy needs to replenish its gas, otherwise it quenches itself. It can't make stars anymore. And the only way a galaxy can get large and make millions of billions of stars is if it has gas to replenish itself. And the larger it is, the more gas it's going to need. So what this is showing is how this is a demonstration of gas forming a large galaxy. And you can see that the disk itself, this feature was in place pretty quickly, but the event of accreting more gas or more galaxies continues well beyond the point where the disk is formed, which you can see here. And of course, if this simulation kept going, the left was another extra coming in. So it's a natural, this is natural. The Milky Way is just going to continue eating galaxies that are smaller than it, keep growing in size, and just litter its corpse, litter the dwarf galaxy's corpse right in the halo, because everything that happens out in the halo, I mentioned that it wasn't very dense out there, it's very diffuse. So when events happen in the halo of the Milky Way, the dynamical scale, how long it takes for these events to happen, is over the course of billions and billions of years. If you're in the disk, of course, there's a lot more matter moving around, and things, original motion or these events that might cause things like streams get completely washed out. But in the halo, that is where you're going to find these objects. And it's not just Sagittarius that's the Milky Way is eaten. Of course, this is the graveyard. There should be more features. Now, this image here is an all-sky view of the Milky Way from 2009. And in the bottom right-hand part of the screen, you should see two features, gaseous type features. And this is the LMC and the SMC. And if you can see my mouse pointer, I hope you can, I'm circling them with my mouse pointer now. So these are two dwarf galaxies. I mentioned the LMC earlier, pardon me. These two are quite prominent in the southern sky, and these galaxies have their own globular clusters embedded in them. And when you look at this image and you look at them in the optical, there doesn't look like there's anything going on. They're just there, looks fine, nothing nefarious going on. The Milky Way is not doing anything to them, right? Well, no. If you look at the SSM and the LMC in the infrared, you can see that they've been interacting with the Milky Way for quite some time. What you're seeing here is hydrogen alpha lines, or hydrogen alpha gas, that is currently being stripped off the two through interactions with the Milky Way. And the situation is a lot more complicated than that. The SMC, the Small Magellanic Cloud, should have made that clear. So Small Magellanic Cloud and the Large Magellanic Cloud, they're also interacting with each other. And they've been interacting with each other, it seems, before the Milky Way got involved. And in between these two galaxies is what we call the Magellanic Bridge. And in there is signs of early star formation. So the elements in the SMC interacting, they're forming stars, but all of that's going to be pulled into the Milky Way anyway. It's quite violent if you think about it. But it's not just, I mentioned that this was a common place. And if you look at Andromeda, the nearest largest spiral galaxy to us, there's a lot more clearer picture of this exact event, this kind of accretion of galaxies, this cannibalism of galaxies. Now the Andromeda, or M31, whatever you want to say about it, it's a good Milky Way analog. And what's a good thing about it is that you can look at it very quickly. You look at the entirety of the system with a few observations. When you're inside the Milky Way, or you're going to cover the same relative size of space. So if you want to look at if you want to look at, well, you're inside the Milky Way is basically what I'm trying to get at. You have to look everywhere, 360 degrees, all the way around you to even begin to map the Milky Way. With Andromeda, you just point a telescope up there for a bit, and you can get the entire system. And that's, of course, astronomers from Edinburgh have done this. And this here is an image of Andromeda, where the Andromeda galaxy itself, or the prettiness, the bar, the gas, and all that, sits well into the center of these purple dots here, which are globular clusters. Now, this image, it shows the black and white density. So the more darker a pixel is in this image, the more stars are in it. And as you can see, there are plenty features of streams in this area, in the halo. Just to remind you, the galaxy itself is only entirely embedded entirely within those purple magenta points. The halo of M31, of Andromeda, extends well beyond that. And not only can you clearly see these streams, much like we saw with Sagittarius, there are globular clusters, these purple dots embedded on or nearby these streams. So if we cannot look at the Milky Way as a whole very easily, if we remember that M31 is a very good analog, then we should be able to look at globular clusters and look at the regions around them to potentially find other dwarf galaxy streams or other remains of dwarf galaxies that the Milky Way is eaten and maybe isn't proudly putting on display. So this leads us to the globular clusters of the Milky Way. So this image is an all-sky diagram with the disk of the galaxy stretching right across the middle in the kind of light blue. And all the globular clusters are these yellow spots on this plot. As you can see, the globular clusters are embedded. They live at all different distances from the galactic disk itself. So you have a lot in the disk, but also a lot outside. And so star clusters, they kind of have, first, they most likely have been formed out of the same gas cloud. They're all the stars in these systems kind of look the same. They all probably have the same metallicity. They'll have the same age, roughly. And they all would have lived and died in that area. But there are some globular clusters that don't kind of walk and talk like the rest. I mean, the idea of a single population of stars doesn't really exist in globular clusters, at least in some of them. The globular cluster of interest that I'm trying to get at here is the globular cluster M54. Now, this is quite a massive globular cluster, and it has multiple populations of stars in it. And in this system, what I mean by multiple population is that there are many populations of stars that have different metal contents. So if you recall what I mentioned earlier, metal can only be created in the center regions of stars. So what is suggesting that this globular cluster, which by all means, if it's in the strictest definition, that it has the same metal content, all the stars pretty much walk and talk the same age, if the stars have different metal contents, then this cluster must have undergone at least multiple epochs of star formation. Maybe they formed as two clusters that are separate and merged together, or they evolved in a very interesting environment, say the core of a dwarf galaxy. And it does happen, M54 happens to sit dead smack in the stream, dead smack in the center of the Sagittarius stream. So that was actually rather easy to identify as the core of the dwarf Sagittarius, dwarf swaddle. And this is, you get you thinking of the analogs of, okay, we know that we can look at globular clusters and look at peculiar globular clusters, one that are like M54, ones that have spreads in metallicity or multiple populations that have different metal content in them, and think that we could search in the area surrounding them. So if there is no stream like Sagittarius, and Sagittarius at this point is the only dwarf galaxy stream that we can see at this point in time, then instead of trying to just blindly search around the entirety of the galaxy, maybe we should just search in the periphery of globular clusters that look just like M54. And I did that. So myself and a couple of astronomers in Australia we started searching for what we're going to call extended structures, so cluster-like stars surrounding globular clusters themselves. And for an example, there's the globular cluster M2 or NGC 7089, which is much like M54 in that it has, I think the count is now 7 different populations of stars. So 7 different groupings of stars that have the same metallicity, all very different, of course, in their own way. So it gave itself to be a prime candidate as a dwarf galaxy core. And there are other things that can suggest that a star cluster or a globular cluster could be the core of a dwarf galaxy, or at least didn't form in the Milky Way. Maybe it's got retrograde motion, so its orbit is different in the opposite direction to the orbit of the galaxy itself. It's another big clue. Well, another red herring that it might not be part of the Milky Way or formed with the Milky Way. But when we looked at NGC 7089 or M2 here with big wide field telescopes and tried to look as deep as we possibly can, we wanted to try and pull up as many stars as we can. What we saw is not a stream, but we saw what we would call a diffuse stellar envelope. So while the globular cluster itself may only be a couple of tens of parsecs in size, the envelope structure that we're seeing embedding M2 and a couple of other globular clusters stretch out to hundreds of parsecs in size, 3 to 4, 5 times greater than the cluster itself. And these objects, these features, these diffuse envelopes that these globular clusters are embedded in are extremely faint. They are primarily made up of lower mass stars, and you can only really see those because they're lower mass, they're fainter. You need big, massive telescopes and observing for a very, very long time to get them. So these objects are only just now starting to appear. And we don't know how frequent they are, how ubiquitous, I think is the word I was after, they are in the Milky Way halo. And are we actually seeing, is this stellar envelope the last shred of the dwarf galaxy that M2 used to call itself its core? We just don't know at this point. I mean, the other option is maybe the Milky Way eats globular clusters as well. I mean, that's totally plausible. Globular clusters themselves are the reason why they've been able to contain themselves together is that they have strong enough gravity. But as a star cluster orbits the Milky Way, as a globular cluster orbits the Milky Way, depending on how far away it is from the disk, the gravity exerted on them by the Milky Way, it changes. And depending on how quick or severe this change in gravity can be, can have a very shocking impact on the structural integrity of the globular cluster itself. Now, I mentioned an object before, Palomar 5, which is the poster child of globular clusters that the Milky Way is currently tearing apart. So in the bottom left-hand corner of the screen, you can see a little white dot with two thin stream-like features coming out of it. Well, we'll bring up this kind of image. I think it suits it a bit better. The Palomar 5 is a very unlucky globular cluster. It is currently being torn apart by the Milky Way. It is estimated that Palomar 5 has lost 2/3 of its mass in its tails, strictly just by orbiting the Milky Way. Nothing else going on. It's happily doing its business. But as the globular cluster hit the disk, it is shocked by the suddenly almost instantaneous change of gravity, and that allows stars to strip. And as Pal 5 leaves the disk and starts heading further and further out, these kind of tail-like features start to form. Because when a star cluster is shocked, these stars can escape the gravitational pull of the cluster just by a little bit. It doesn't need to be much, but as soon as the balance is shifted and the gravity of the Milky Way is taken over, it can start pulling the stars apart. They leave with almost the same velocity that they had within the cluster. So that's why these stars stay quite close. And as time passes and the cluster takes more and more orbit, there's more shocks, and it can stretch and stretch and stretch. Now, the reason why it's in this kind of S-ish looking shape, or it comes out in these streams, is that the star cluster, once it's shocked, a star cluster kind of puffs itself out until it feels where its gravity is, can keep it all together. But there are 2 points known as Lagrange points. And these points are considered to be gravitationally neutral in a two-body system. Each two-body system, Earth and the Moon, Earth and the Sun, a star cluster and the galaxy, have 5 of these points. And there are 2 points that exist in the system that are close to the cluster itself, and the stars can drift along there. So that's why we have this kind of two stream-like features coming out. So not only are dwarf galaxies falling prey and being torn apart by the Milky Way, but the Milky Way is also strong enough to pull apart its own globular clusters. Now there's about 160 odd globular clusters in the Milky Way. So it is unclear how many the Milky Way has actually eaten as time has gone by. So here's, and another thing that's briefly mentioning, there are streams again that have no progenitor. We don't know if they belong to a globular cluster or they belong to a dwarf galaxy. We have no idea. GD1 is another one of those, which you can see in this stream, field of streams image again. Luckily it's labeled, so it should be easy to see. Now, let's have a quick recap of what we know about the Milky Way and its substructures in the halo. There is a large dwarf galaxy, Sagittarius, that's been torn apart. We know that for sure. There are globular clusters that have diffuse stellar envelopes around them that we aren't exactly sure how they're formed. They could very well be embedding, they could be the last remains of a dwarf galaxy that the Milky Way is torn apart, because these objects, these features are typically found around globular clusters, that are peculiar, they're much like the globular cluster we see at the center of Sagittarius. There are tidal tails, much seen around Palomar 5, and there are plenty of globular clusters that show these features. And then there are streams and features like clouds that have no obvious progenitor. And of course, often pandas, there are multiple streams, as I showed you before. But all this can be torn apart now because of Gaia. So hopefully a lot of you have heard about Gaia. It sits at Lagrange point 2. So I think it's behind us on the orbit of Earth's orbit around the sun. And this has been a game changer, frankly. Gaia had a very very ambitious plan, and that is to make the largest three-dimensional map of the galaxy by surveying about 1% of 100 billion stars. Have they managed to do that so far? Yes, they have. Let me give you an idea of what's happening in Gaia at the moment. They've observed 1.8 billion stars, and about 1.5 of them have what we call a 5-parameter solution. Now, what that means is they have positions, light ascension and declination, parallax, which helps you estimate the distance to them, and proper motions. And proper motions are their motion across the sky. It's only very, very small because these objects are very, very far away. But if you look at it over multiple years, then you can actually start to separate out co-moving groups of stars together. And I guess you can tell where this is going. What has Gaia presented to us in regards to dwarf galaxies? So we've been able to find things like Sagittarius because everything is visually grouped together on the sky. But there are some things you can't see because maybe the event happened so long ago that it's been spatially completely washed out. This plot here indicates the motion, the cylindrical motion of stars in the sky from Gaia. And there's a feature here, it's the velocity in the radial, velocity in the rotational axis of the galaxy. You can see this kind of bendy-like feature just here and here, where this spot here is the galaxy itself. So the dark spot around 200 in V phi in both images is the galaxy, but there's some other feature unexpected to appear, which is right across the zero, kind of bends. So in 2018, just before the second data release of Gaia came out, Vasily Bekirov and co. found a new dwarf galaxy. And because of the shape, they called it the Gaia sausage. So Sagittarius, Gaia sausage. Simultaneously, though, a different group of astronomers found evidence for the exact same galaxy. Now, again, this is using the proper motions from Gaia, as well as line of sight velocities from another source, because Gaia doesn't supply all of that. In the left is what was done beforehand, the state of the art of this plot, which shows the velocity in the y direction, and then against the velocity of the magnitude of the velocity in the x and z direction, when you look at the Milky Way as in x, z, and y, kind of like x, z, y. But with Gaia, those pixels become a lot clearer. And while the disk and the halo are pretty much exactly the same, there's this blob at around Vy equals 0. And they called it Gaia Enceladus. Well, this is the exact same object as Gaia sausage. So here's a fun little thing that astronomers have done. They've named this object the Gaia Enceladus sausage. And I'm not joking. There's been a big debate on whether the term sausage should be in there at all. And even though the people who discovered it first called it the sausage. But anyway, quickly moving on from that, when you consider the proper motions and you tie that into line of sight velocities, all of a sudden, anything that's not coherent in space, in RA and DEC, and of X and Y, become grouped together in velocity space, in energy space, and angular momentum space. So what this plot here shows is where they're finding new features, new dwarf galaxies that the Milky Way is eating, which has been completely shredded, and you can only see this left there. Sequoia, Gaia Enceladus, Helmi streams. Things like Thamnos, not too sure about that. And of course, what we now know, thanks to Gaia, that there have been 5 major dwarf galaxy accretion events in the Milky Way's history, starting with the Kraken, the Helmi streams, Sequoia, Gaia Enceladus, but not sausage, because this was made by the group who called it Gaia Enceladus, so take with it what you will, and of course Sagittarius. But here's the thing. Yes, 5 major collisions, but strictly speaking, they've only contributed about 0.001% of the total mass of the Milky Way. So a lot of the Milky Way still formed in situ. It still formed as a monolithic collapse of gas. But the halo itself has had most of its contribution by these 5 dwarf galaxies. And we, as far as what the field of streams looks like now, this is Gaia, it's pre-Gaia, this is now post-Gaia. And we're finding a lot more streams. The orphan stream is pointed out here in Palomar 5, a couple of ones that are worth noting, Flimbuthal and Joel here, not sure how to pronounce it, a couple of streams that are very clearly dwarf galaxy streams. The others, not too sure, but there's a lot here that's now popping up. And in fact, a more complete picture looks like this, with Sagittarius running right across the middle, and all of these other stripes that you're seeing across the image here are labeled, and they show the footprint of all the different streams. So we've come a very, very long way in trying to understand how the Milky Way formed. And the key is to try and find dwarf galaxies and look at streams, because not only can we piece together how our galaxy formed by looking at those objects, how many events had happened, how old it is that we can also get an idea of the mass of the galaxy, because how much mass that we have can give us a lot of imprint onto things like dark matter and stuff like that. And I think I am approaching time, but I'm going to give you a quick epilogue here. Yes, we're talking about the Milky Way eating smaller galaxies and littering their corpses on display for us all to see, or in some cases hiding them very, very well, that we needed to get a multi-million-dollar instrument into the sky to find out. The Milky Way is going to eventually collide with M31. 3-4 billion years from now, they will collide, and over time, these objects will, as they collide, there'll be flashes of star formation, and a lot of hot blue stars will be formed, but those will be short-lived. And after the collision, when the two masses finally relax, there'll be nothing but a sea of red dwarfs, and the galaxy will be nothing that we see today. They'll just be red dwarfs for as long as red dwarfs live, trillions of years. So thank you very much. I hope this has been easy to follow. I'm happy to take any questions you may have.
Pete, that was fantastic. Thank you so much. That is just stunning data, just stunning data. I feel quite sort of dazed, actually. I mean, it is just remarkable. This field has obviously leapt along incredibly quickly.
Yes.
Mm-hmm.
So the release of Gaia, I cannot emphasize how important Gaia has been. The Gaia space mission, all with, as you saw, 1.5 billion sources with on-sky motions, has just completely changed the game. Like, for example, the Sagittarius galaxy was discovered by accident, by looking at line of sight velocities. They were just looking, oh, look, here's this radial signature that we didn't know existed. Let's see what this is. Trace it out into a galaxy. But because these objects are faint, and stars in these newer objects are so faint, and they look very much like standard Milky Way stars, you really needed the on-sky motion to show everything that moves together to really bring it out. It's been insane, just how much has come out.
Astonishing. Have you got questions coming in, Dave? Or
yeah, we've got one question from Scully Brooks.
Yep.
He says, in the simulation, when you showed the globular cluster, it looked quite big and it got pulled apart quite spectacularly, but the disk of the Milky Way didn't seem to be perturbed very much at all. Is that something in the simulation, or is there a reason for that?
That is just for that simulation. It was done 2005-ish. That's one that I just kind of pulled off the internet. But in that instance, the Milky Way was fixed. It was kind of, in that simulation, there was a placeholder to show the size of the Milky Way, but the potential for that was considered to be static. It is very important to know that, of course, in these collisions of galaxies, the massive one does get perturbed. And my co-workers have recently released a paper about this and how the Large Magellanic Cloud is warping the Milky Way right now. And we can see its effects not only in the position of the disk and how it kind of fluctuates and warps, that the certain streams, such as Orphan, are showing signs of being warped as well. So in that was a very simplified simulation, you are dead right. The galaxy should be twisting and warping as well.
Right. Yeah. As you mentioned, the Magellanic Clouds, I did have a thought that there is this bridge between the small and large clouds. Is it possible that they were at one time a combined object, and these are just two cores from, or a split core from a single dwarf galaxy that got torn apart?
It's a very good question. I don't think anyone has explored that possibility.
Yeah.
They do show distinct ages. So I guess that situation is unlikely. I think there's a good couple, I think that's 1 billion or 2 years. The SMC is quite a young galaxy, I believe, in comparison to the LMC.
Yeah. And I was also interested in the use of the Gaia data, because that kind of came in at the end of your talk there, but are you expecting a lot more interesting results on data release 2 and data release 3, when we can really get a lot more information on proper motions, and we can see things that are moving sort of co-planarly or co-linearly?
Yeah, the most recent data release was the early data release 3, which came out in December 2020. Yeah. And the fruits of that was looking at, there's a couple of papers on, which admittedly I haven't read as much detail, that have looked at the anticenter of the galaxy, as well as looking at the Large Magellanic Cloud and tracking its debris to studying solar system objects. So already we're seeing the second data release, the early third data release, proved to be quite fruitful. And as for my own research, I am searching for more extended type structure, like tails surrounding globular clusters, and I'm already seeing some very huge features that were not shown, that weren't obvious in the second data release, because the precision in this motion has been lowered by a fifth. So it's only going to get better. I think a lot of analysis in regards to discovering things like the Kraken, the Gaia Enceladus sausage, however you want to call that one, Sequoia, this will all be refined. And what's going to be particularly exciting is Gaia, when it is combined with upcoming large-scale surveys that are going to be able to fill in the gaps that Gaia hasn't been able to do. And that is specifically line of sight velocities. The Gaia can only measure line of sight velocities for the brightest of stars. But we've now got our hands in projects that are now going to fill in that gap. And that's going to be amazing. Because as soon as we can start hitting fainter stars, we're going to get larger samples, and we'll be able to trace these events to unprecedented depths. Haven't seen it before.
So is this work such that it would upset some of the sort of dearly held beliefs in cosmology that we have at present? Because some of the work you were describing with the formation of the global clusters sounded slightly fundamental.
It has potential to. This is the excitement of this kind of data set. Before, as I mentioned briefly, before Gaia, Sagittarius was the only thing. We thought the Milky Way only had one formation, and therefore it only brought in maybe 10 less globular clusters out of the 106 that we have. And then all of a sudden, you've got so many dwarf galaxies, which astronomers are tagging one cluster to multiple ones, saying it belongs to this one. No, this globular cluster belongs to this one. So we're already seeing this kind of tug of war between which is the best description of the Milky Way's formation. And only until recently have they been able to start touching on cosmological matters such as quasars, dark matter, as there is the problem motion hasn't been accurate enough. But come the full data release, which is going to release, I think it's releasing spectra as well, you can expect something pretty groundbreaking come out of that, as far as far universe, high redshift type stuff.
Right, we've got another question on the YouTube chat. There's lots of people complimenting you, thanking you for a very interesting talk as well. And
thank you very much for having me.
And the question is, why is the Enceladus stream called the Enceladus stream, the Gaia Enceladus? Not worrying about the sausage part, but why Enceladus?
That is just what they've named it. A lot of astronomers kind of take a bit of liberty of how they name things. Yeah. But a lot of people do try and stick to some kind of naming convention. So I can't say as to why Enceladus has been particularly, why that name has been labeled, but a lot of the streams, things like Fin Beautiful and others that I can't name, they just decided to name them all out of Norse gods for no reason. They're just, this is the names we're going to tell them.
Oh, yeah.
Something like Sagittarius had made sense because where it was discovered was in the constellation Sagittarius.
Yeah, apparently Enceladus was the son of Gaia, so it's possible that it's because Enceladus, Gaia.
Oh, that's amazing! Yes, I'm going to choose to believe that that's where this all came from. That sounds delightfully poetic.
Yeah, I'm not sure about the sausage bit though.
That name has had too much conversation around it, frankly.
I mean, it's clear that a lot of the data that you're able to get now is really quite stunning. What would you like to be able to get your hands on next to move this on?
Oh, I would love to get my hands on that last remaining line of sight velocity. So looking at the star and seeing how far it's moving respect to me, because we only have the 2 dimensions on the sky. We need that third. And that would let us depict what's going on in the, so for me, what's going on in the outer regions of globular clusters. What we're seeing, is it rotating? If so, how much? And how much it's rotating and how fast the stars are moving with respect to the others can tell us whether there's dark matter around star clusters, which we're not quite sure. Typically we think no, but some of these extended features can't exist without dark matter, so maybe need to find out. So we just need that last line of sight, and we should get that in about 3 years, fingers crossed.
Okay. And enough of that will satisfy you for what you want, yeah.
When you have 150 odd globular clusters to look at, it'll keep me busy for a very long time.
That is just terrific. I am very, very grateful to you for giving your time and coming to speak to us on this. It is amazing work. I mean, just really superb, and beautifully presented as well. So interesting and nicely done. I mean, it's quite a good combination, really.
Thank you very much. It's my pleasure. I wish I could have been there to meet you all in person in Dundee.
I know, but you see, once you get your line of sight observations in, we'll definitely will be back in the mills and you can come and visit us there. So that would be really good. Really good indeed. Absolutely. But thanks very much, Pete. That was a superb talk. Really lovely.
Thank you very much.
Yeah.